today onwards, we are going to begin. Just let me put my phone on silent. Sorry. Yeah. So today we are going to begin with our sessions on science and technology. And from here on, the next 11 classes, we are going to look at the various aspects of science and technology, the various chapters, what kind of questions can come, what kind of questions have come. All these kind of things are some things that we are going to look at. All right. So, but before we move on to our chapters, first we'll look at the strategy for this examination, because when you look at this particular paper, this subject, it's very different from many of the other subjects that you're going to learn. So that's why it needs to be very clear in your minds as well that what do you need to focus upon. We'll also take some examples of how questions come and what do we expect in the upcoming examinations as well. So all these are the things also that we are going to have a discussion on. All right. So to begin with, to understand the strategy, first let's have a look at the syllabus, of course. So before for understanding any subject for any paper, you need its syllabus. You need to understand its syllabus very well, because unless and until you know the syllabus, you cannot go further. You cannot be blinded. You cannot be very blind and just think that, okay, fine, there is a subject called science, and whatever comes and whatever chapters I see, I'll just go on to read it. There are a couple of things that become very, very important for you to understand what to read and what not to read. First, of course, is the syllabus. And second is all the previous year questions. These are two things that define the syllabus for you. Otherwise, the names of the chapters, the names of the subjects will not give you the holistic idea of what needs to be done. So if you need to really understand what needs to be done in any given subject, not only about science and technology, but for any given subject, you need to understand the syllabus and you need to just have a look at all the previous year questions. I'm not saying that you need to know the answers to all these questions, but you need to understand, okay, fine, this is where the questions have come from, or these are the kinds of questions that they have been asking. So for you to understand all these aspects becomes very, very crucial, so that you can plan your subject accordingly. You can make the notes and everything accordingly. So that's why syllabus, first of all, becomes very, very crucial. Now, when you look at the syllabus of science and technology in prelims examination, nothing really is very clear about what needs to be read. So if you see, the only thing that they have written is general science. Now, when we say general science, we don't know how general this general science is. Where do we begin and where do we stop? Correct. So that's why we do not really get an idea. One thing that I have just added from my side is current events of national and international importance. That also becomes very crucial, correct? Because all the current affairs, all the things that have been in the news, all these things become very, very important. And you will see that many a times the questions that come, especially in science and technology, they are related to the static and the dynamic parts of the syllabus, both at the same time. So that's why current affairs becomes very crucial. But overall, prelims syllabus does not really say anything. Look at the main syllabus. There are 3 points that have been mentioned in the main syllabus. What are these? The first thing is science and technology, developments and their applications and effects in everyday life. Meaning that whatever science and technology we are using, which in one way or the other affects our life. Now, probably everything a part of science is almost everywhere. And we'll also see this at a later stage. There are questions also that have been asked from this particular point, but we'll look at it later. But you all know, right, that there is no part of your life which is untouched by science in one way or the other. There are things which are very, very basic to your life, which are related to science, where science is affecting your life. And then there are the advanced parts of science, which is affecting the technology at a global level. The second point says achievements of Indians in science and technology, indigenization of technology, and developing new technology. All right. So achievement of Indians. Now understand this, that when they say achievement of Indians, the meaning of achievement of Indians is achievement of Indians. It's not about a particular scientist. It's not that they are going to ask you the biography of a scientist. They're not going to ask you about the schooling, the college, the birth and the death of a scientist. No, because this is a science paper. If those questions had to come, it will come in your GS paper 1, history, correct? So they are not going to ask you biography of a scientist. So you have to think of the achievements of Indians, meaning the entire scientific community. How have they done something for India? For example, space technology. We know how far we have reached in space technology and how good the space technology in India has been. The role of ISRO in the development of space technology, in the advancement of space technology. So it's not only due to one scientist, correct? Yes, there are some scientists which have been pioneers in this particular segment, but it's not only about just one scientist or a couple of scientists in that sense. It's about the entire scientific community which has had a big role to play in the development of science and technology in India, right? And then similarly, indigenization of technology. Okay, so if I ask you uh, about what is the meaning of indigenization, can you tell me what is indigenization? What do you mean by indigenization? Yeah, local Indian version to make it suitable for our own country. That's correct. Good answer, Garvit. Yeah, so more or less, many of you have written the same thing, right? So it is localization, correct? It is localization, or basically adopting a technology that will suit the requirements of our country, correct? So technology may be something that has been developed anywhere, any part of the world, something that we are adopting, something that we are looking at, or we are using in one form or the other. So that is how indigenization of technology has to be understood. That's correct. So most of you have given the correct answer. And then developing new technology. So anything new technology, any new technology that whether developed in India or maybe developed somewhere else, but also being adopted by India. So all these new technologies at a global level also become important. And we'll take examples. Don't worry. Right now, I'm just giving you a basic structure of everything. We'll discuss in details as we move on to all our chapters. Now, the third point is where actually they have mentioned everything. All right. So, the awareness in the fields of IT, space, computers, robotics, nanotechnology, biotechnology, and issues related to intellectual property rights. So, these are the things that we are going to actually discuss as a part of all our chapters. And you'll find that even in your prelims paper, the questions that come, many of those questions are actually related to these areas only. So that's why all these topics or all these keywords that have been mentioned here, all these keywords, they become important for your examination, both at prelims as well as at mains level. All right. So, sorry. So if you look at all the topics that we have to discuss, these are going to be your chapters. Now, if you look at all these chapters, in this, the first two chapters, space and energy, my understanding is that these are the chapters that are going to be the most important for you at prelims level as well as at mains level. I would say that these are going to be the most important chapters, and we can expect that at least one question in prelims examination, and in mains examination also at least one question could be asked from these two chapters, because a lot happens in these two areas. Space technology, every day you will come across some news or the other which is related to space technology. Similarly, we know that how much we are spending on energy, on alternate sources of energy, whether India or other parts of the world. Everyone is investing in energy, and that makes energy a very, very important chapter. Then after that, we have biotechnology, not a very big chapter, because first two chapters are very big chapter. I mean, these two chapters probably will take the next 5 days. These are very big chapters. And after that, all the other chapters are not that big. So, biotechnology, again, from prelims and mains perspective, very, very important. Nanotechnology, I would say more important from prelims perspective. Primarily important from prelims perspective, but we cannot say that questions won't come in the mains examination. But we have seen that the numbers are pretty less in mains as compared to prelims. Then robotics and artificial intelligence. Now, this is an area that primarily will be important for prelims examination, But this year we saw that artificial intelligence based question also has been asked in your mains examination as well. And we'll discuss that question when we go to the chapter of artificial intelligence, because we know that artificial intelligence has become one of those areas that is the fastest developing technology right now. There's no other technology that is in the news or maybe around you so much as artificial intelligence is. Everyone is today talking about AI in one form or the other, whether in a positive sense or in a negative sense, but we do discuss this. Then IT and communication, again a chapter I would say primarily important more from your prelims perspective. Then these two chapters, defense and diseases, these two chapters, these are chapters where whenever questions come, you'll find that the questions are always based on current affairs. More than the static areas of these topics, the dynamic areas or the current affairs of these two topics matter a lot more. All right, so that's why these two topics I would say you have to ensure that you base your preparation on current affairs. All right, these two chapters have to be current affairs based. And then intellectual property rights is a chapter which is primarily important for your mains examination, but sometimes questions can come in prelims also, they have come. But you have to understand that this is a basic understanding of all the topics, and these are the chapters that we are going to discuss in your entire segment of science and technology that we are going to discuss in the coming few lectures. Now, if you look at the basic trend of the number of questions that have been coming, so every year you'll find that at least 12 13 questions come every year. A maximum of 14 15 or up to 16 questions come in your prelims examination. And these are the topics which I would say that these are the direct questions that have been coming in your examination. Apart from these, there are some mixed questions as well, where maybe a couple of statements are related to science, a couple of statements are related to maybe environment or geography and so on. So in this manner, we see that at least 12 13 questions every year and a maximum of 15 to 16 questions everywhere in your prelims examination have been coming. Now, one thing to note here, especially when it comes to the prelims examination, science and technology as a chapter, or rather as a subject, is very, very crucial. Unfortunately, what we have seen over the years is that this is one of the most neglected areas as well, most misunderstood areas as well. And we often see that there are candidates who just go in the examination thinking that even if I leave science, nothing happens. This is where they are wrong. This is where they have been proven to be wrong, and in the next time or in the next attempt they go very heavy on science when they realize that the mistake that they had committed. This is not an area that can be neglected. And understand one very practical aspect of your examination here. Sorry, I'm a little uh, unwell, so because of that I'm coughing. So understand your prelims examination. Your prelims examination, first and foremost, has 100 questions. And if there are 15 questions that are coming from science and technology, it's a big part, 15% of your paper, right? How much time are we taking to complete this 15% of the question paper? 11 classes, that's it. 11 classes, the classes that I'm conducting, plus you will add some current affairs, and current affairs is something that you add for any subject for that matter, right? So this is enough for you to score good, to get at least 80% of the questions right. And that's a very big thing, because when you look at the, let's say, return on investment, the investment of time on each and every subject, this is where in the prelims examination, science and technology becomes a make or break paper. Because in the mains examination, I understand the number of questions are pretty less, but in the prelims examination it plays a big role. But unfortunately, we have seen that many aspirants, because they have been, either they have been guided wrongly or they have a wrong notion, or maybe because of lack of resources, etc., we have seen that this has become a neglected subject. But you can't do that. You really can't do that, because you cannot just say that, okay, fine, I have 85 questions, and out of 85 questions I'll do correctly 60 65 questions and I'll be able to crack the prelims. things are not, I mean, the world is not that simple, that it will not happen. And that's why you have to be prepared with all the 100 questions. You have to be prepared with every part of the syllabus that's in front of you. So that's why understand its role in your prelims examination more than anything. In the mains examination, what we see is that every year the number of questions are pretty fixed. 3 to 4 questions have been asked every year. So almost 35 to 50 marks generally in your prelims, sorry, in your GS 3 paper, you'll find that it comes from here, from science and technology. And these are very easy questions. We'll take examples chapter by chapter as we move on to those chapters. So you'll find that the questions at mains level in science and technology are easier as compared to the questions that come in your prelims examination. All right, so prelims can be little tough, and that is why we are preparing for it. And in the mains examination, you'll find that the questions are much simpler as compared to prelims. Now, what are the areas? And this is very crucial for everybody to understand, that where do the questions come from? What are the areas from where the questions are being asked in science and technology? First, any major scientific breakthrough or the running stories in the field of science and technology. Anything that is being discussed. Right now, just think of certain topics. And I'm very sure that there are news items that you've come across and you know that these are areas that become important. And you'll find that more often than not, questions will come from these big areas. Hardly any questions are coming from areas that were hidden, areas that nobody knew of. Yes, there will be a couple of surprises, that's why it is UPSC. Otherwise, you'll find that most of the questions that come, they come from areas which were highlighted areas, especially in science and technology. So you can think of some topics. Can you suggest some topics right now? Yes, Chandrayaan, correct. Artificial intelligence, Gaganyaan, Nobel Prizes, yes, correct. Quantum dots, yes, that's related to Nobel Prize. So, Aditya L1, correct. 5G, correct. Lagrange point, correct. Semiconductor. So, you also understand, right, that these are topics which are being discussed so much that if a question comes from here, it won't be a surprise for you, correct? And that is where you'll always see that the questions come from. Questions are not coming from hidden areas. Please make sure that you know this. And this is where, when you read your newspapers, while you read your newspapers, especially from science and technology perspective, understand this one aspect of your newspaper. In the newspaper, what you'll see is that there are also a lot of small topics of science and technology. That maybe there is this corner column of your newspaper where there are small articles related to science. You might have noticed this. Now, most of the times, these kind of areas or these kind of small topics or small articles, they're not important. We don't expect questions to come from there, because most of these kind of articles, these are research based articles. All right, these are research based articles. We don't expect questions to come from research based articles. Why? Just understand how much of research is happening in the world right now. There are so many science universities across India, then across so many other countries like India. And just imagine the amount of research that is happening. And then there are certain journals, there are certain magazines which will just publish those researches because they are interesting to read. So that's why in the newspaper articles also, these kind of topics or these kind of small articles that you have, these are interesting areas to read. And that's why they are in the newspaper. Because understand, fine, that if you're reading the Hindu or Indian Express, it's not that only the UPSC aspirants or the civil services aspirants read the newspaper. There are others also who are reading the newspaper. So obviously they have to find articles, science based articles, which are not boring, which are not too technical to read, which are interesting to read. And that's why these kind of articles will come. So you have to understand that not everything is important. Not every article related to science is important. That's why I've written here major scientific breakthrough and running stories. Questions have to be expected from them. And then all the static areas which are related to these breakthroughs or these running stories. The basic concept behind it, that needs to be understood. And I'll explain you as we go in the chapters. These kind of points will become clearer for you. Then government programs and initiatives, goes without saying. Any ministry, whether science related, whether any other ministry related, they always are important. And one thing is consumer oriented technology, the technology where we see that in one way or the other consumer is affected. A very simple example is your 5G technology. Correct. 5G technology is going to affect each and every consumer. So that's why 5G as technology for us in the examination also becomes very important. So I've been saying this for the last couple of years that I'm expecting that a question would come in your prelims examination from 5G. Until now, it has not happened. In 2022 classes also I used to say this. In 2023 batches also I used to say this. Now for 2024 batches also I'm saying this, that 5G as a topic is going to be very, very crucial. I'm just expecting it's just a matter of time that they ask a question from here. Until now, they haven't. So that's why be prepared. 2024 prelims examination, I'm again saying, I've been saying this to the past couple of batches as well, that I'm expecting that a question should come from here. So that's why these are areas from where we expect that questions can come. Now, one last thing before we move on to our chapters is all about our sources, that what are the sources from where we get everything related to science and technology. First source would of course be newspapers. Either you read the Hindu or the Indian Express. One of these two newspapers, these, I mean, from science perspective, these are the best two newspapers. They cover everything that is relevant, so always good to read these. Then you have PIB, or Press Information Bureau. So Press Information Bureau, you can say in a manner, is the government mouthpiece, that everything that the government is doing, every new project, any new scheme, any new initiative, all these things will be published there. So on PIB you can go and you can select ministry wise also, that for example if you select Ministry of Science and Technology or Ministry of Atomic Energy, so then there, or Department of Biotechnology, you'll see that everything that they have announced or they are doing, you will find everything very easily there. Then the magazines, Science Reporter, Down to Earth, Yojana, Kurukshetra. Now, these magazines, I wouldn't suggest that you should read from cover to cover. You always should be very selective while reading this. Anything that is remotely related to your syllabus, only those are the areas that you should read. Apart from that, other things, don't read it. You don't need to read it cover to cover, especially Science Reporter, because Science Reporter could become a very technical magazine for you. So it's not very easy that you would be able to follow this magazine so easily. So that's why depend on the webinars for this, because in the webinars we are covering everything related to your syllabus in especially in the Thursday webinars. In those webinars we are doing everything possible from the perspective of whatever is required from these magazines. And then lastly, NCRTs. Now, from the perspective of the NCRTs, just understand this. I mean, from science and technology, what do we need? My suggestion, class 6 to 8th NCRTs. Read class 6 to 8th NCRTs. Never read a class 11th or a class 12th NCRT. Please don't do that. Because class 11th and 12th NCRTs, they are very detailed and too technical, especially for anyone who comes from a non-science background. Even the people who are coming from the science background will tell you that reading class 11th and 12th science NCRTs is not similar to reading class 11th and 12th geography or history NCRTs. It is going to take a lot of time. I mean, if you practically sit today to read a class 11th NCRT book of physics, chemistry, or biology, it will take you 6 months to cover them. So don't do that impossible task. Class 6 to 8th NCRT is very crucial. Apart from that, from class 9th and 10th, selectively there are certain chapters that can be done. One, there is a chapter on force and laws of motion. Then there is a chapter on gravitation. Then there is a chapter on structure of atom. Then there is a chapter called as fundamental unit of life, which is about the cellular structure of our body or any organism. So fundamental unit of life. And then there are a couple of chapters related to the human body. So I would suggest that these are the only chapters that you should look at from class 9th and 10th NCRTs. Apart from that, reading class 6th to 8th NCRTs are enough to cover your basics. See, primarily we are not expecting questions to come from here. All right. If you look at the past papers, you look at the past 10 years of question papers, and you'll find that hardly there are 4 or 5 questions that have come these 10 years combined. Out of almost 160, 170 questions, there are almost just 4 or 5 questions that have come after reading all these NCRTs. So that's why don't read it from the perspective of expecting something in the paper, but just to clear your basics well. All right, that's the only purpose that these NCRTs will serve. Anyway, we are going to discuss most of the things related to, or whatever has been covered in these NCRTs, a crux of it, while we go to a certain chapter which is related to that NCRT book. But if you feel that you're not good in science, or if you have reservations, and I know that there are a lot of you who have reservations against this particular subject, so if you belong to that group, then class 6 to 8th NCRTs, if you do that much, it's enough. All right. So before moving on, so this was about the basics, the strategy of what we need to do and what not. If you have any questions, all right, for me, before we move on to our first chapter, that is space technology, if you have any questions, please let me know. I'll look at your questions first, and then we shall move to our first chapter. Okay, I have one question for you. I want to understand how many of you are from science background. Science meaning science, medical, engineering, etc. How many of you from commerce background? How many of you from arts background? I'm just launching a poll just to understand. But I just want to understand. Hmm. 30% from this question does not hold any ground in this classroom, and I'll tell you why. First and foremost, the chapters that we are going to look at, even if you are from science background, you probably would have never seen that chapter. For example, let's say something like a nanotechnology. Unless you are from that particular branch of engineering, let's say mechanical engineering or maybe electrical engineering, then only probably you have heard about nanotechnology or read about nanotechnology. Otherwise, nobody knows. Same goes for many of the other chapters. So that's why, whether you are from arts background or commerce background or science background, doesn't matter, doesn't really matter in the context of what we are going to learn and what UPSC is going to ask. Yes, of course, people who are from science background, they might have some background, they might remember a few things, so for them might be connecting becomes easier, but even that will have no effect on this class. So I just want you to throw this notion out of the window before we begin, that neither do I want people from non-science background to feel that okay, this is a technical subject and going to be difficult, and nor do I want the science students to be overconfident, because I've seen this happen. So that's why, don't worry, whether you are from this side or that side, doesn't matter. Right. So any questions if you have? would be, see, there are multiple ways in which we are giving you current affairs. There is the daily Hindu analysis that happens every day in the morning. Then there is the PIB analysis, which is available on your Byjus exam prep app. Then there are these weekly webinars that we are doing. And then there is the monthly magazine that you get. So there are all these sources, correct? You have all these sources. Now, priority one should always be given to a daily source. If you can't follow the daily source, then move on to the weekly source. If you can't follow the weekly source, then monthly source. Monthly source should not be the primary material that you read. Understand this, that every day there is 1 hour lecture that is happening in the morning, which does the news analysis for you, correct? So when we make a weekly video out of it, obviously it would be much more compressed, correct? We would have selected few topics, we would have uh, thrown away some of the topics, and then in the monthly magazine, obviously it would be a much more compressed version of the daily or the weekly resources. So that's why, I mean, in this order, if you can follow the daily current affairs, please do that. If, let's say, for time constraints, you are in your college, you are working somewhere, because of these reasons you can't, then weekly resources. If even weekly resources is not possible for you because of paucity of time, then monthly sources. All right, so please make sure that you do this. So many of you have asked about whether PPTs or books or what to do and how to make notes or whether to make notes. So I'll tell you something. In this entire classroom, or is this the module that we are going to discuss, science and technology, everything what we are doing in the classroom plus current affairs, that's it. No need to go to any other resource, no need to go to any other book or external resources, etc. Not required. Just focus on the classroom. Please make sure that everything that I'm going to tell you in the next few classes, in the next 11 classes to be exact, please follow them. Plus current affairs. Current affairs, whatever source you are using, whether it's the daily Hindu analysis or the weekly webinars or the monthly magazines, these two together will be enough. Last year, I'll give you an example, and it's not to boast about anything or something like that. Out of the 12 questions that came in science and technology, 10 questions were done. 10 questions came from whatever we had done in the classroom plus whatever current affairs sessions I had taken. So that will be enough for you. So please make sure that you focus in this class, because that will make the crux of everything that you're learning, and that makes your life very easy in this subject. So just focus on the classroom and the PPTs and everything that we are doing. Now, notes wise also, a lot of things are already written on the PPT, plus all the things additional I'll keep writing on the PPT itself. All right, so that annotated PPTs can become the primary source for your notes. But if you have a habit of writing, let's say if you are somebody, I mean, I am somebody like that, that I always rely on what I write. So from that perspective, if let's say you belong to that group, then fine, you keep making the notes along with the classroom, along with the annotated PPTs, etc. That's it. So nothing additional. How do you make notes? Either take a notebook or take blank sheets of paper. If let's say you are making the notes in your notebook, then at the end of every chapter, please make sure that you leave some blank pages so that you can add current affairs chapter wise. Current affairs, never do it date wise, always do it topic wise. So that's a topic wise, so that at the end of the chapter, just leave out some 10 pages, etc., so that whatever happens in the next 6 months or in the previous 3 4 months, you can keep adding all that current affairs there. Some of the bigger news will anyway keep on discussing in the classroom, plus there are some smaller segments that you have in your current affairs, or something that is also going to come, because we are in the month of November right now. December, January, February, March, April also you have to add, correct? So that's why just leave some pages like that, and if you are making notes in blank pages anyway, you can add those pages at the end. So many of you had a pretty similar question. Class 6 to 8th NCRT include 7th or of course class 6th, 7th and 8th. Is it true that all the options in prelims from science and technology are mostly correct? Not every time, but yeah, in I'll tell you when it is and when it is not. When we take those examples, I'll tell you. You go to ncrt.nic.in, the ncrt website. There you'll find that there is one portion called as publications. If you go to publications, you'll find that pdfs of class 1 to 12th are available. You go to the specific class, select the subject, and you will get the pdf, downloadable pdf there on the website, free of cost. Just focus on the classroom, please. Just focus on the classroom. Forget about any external source. Just the classroom. Add current affairs to it. Page of your Byjus exam prep app itself, you'll find the PIB analysis. So just go through it. You should read it, even if you even if you feel that you are strong in the subject. Even then, I would recommend that you should read it once. Webinar amount of time you have. If you didn't gain that guarantee, sometimes we have seen that 12 to almost 10, 12 questions from static parts have come. Sometimes only 3, 4 questions from static parts have come. So not for the pattern. Always the same thing will happen this year. Or doesn't mean that, okay, last to last year this had happened, so one year they will skip, another year again they'll do that. 25, 26, 27, etc. Current affairs, if your question is about current affairs, begin your current affairs 15 months before your prelims examination. All right. So if you're writing, let's say in May 2026, then begin your proper current affairs preparation from March 2025. Before that, only the biggest of the news anyway you will read, but don't go into the details of the news before that. The last 12 to 15 months is more than enough. Most important chapter. The most number of questions from science and technology, they come from space technology portion. So that's why space technology, there is no other chapter which is as important as space technology. Also, when it comes to space technology, there are few topics that can be difficult. There are certain topics that can be little difficult to understand. So as we keep going, if you have any doubts in the breaks, I'll give you time whenever we are having breaks. So for example, let's say probably around 6:45 we'll take a break. So at the time of the break, you just write down all the questions that you want to ask. After the break, I'll come back, I'll answer all your questions, and then we'll move forward. So this is how we'll keep going, because I'll not have the time to look at each and every question while I'm teaching, because it also breaks my concentration if I do that. So that's why when the breaks happen, at the time of the breaks, every question that you want to ask, please ask them there, and I'll take every question there. All right. So please do that. And some of the areas here can be a little difficult. If you have any questions, you can just keep on asking me to repeat also if you want, and we'll keep doing that to ensure that you understand things conceptually. Understand this very well, that things have to be understood conceptually in this particular chapter. And uh, when it comes to this chapter, there are two parts to it. The first part will be more of space science, and the second part will be more of space technology. So first part will be about universe, the composition of the universe, the celestial bodies, all these things. And then in the second part, about satellites, the application of satellites, about ISRO, about the various missions. So those, that will be the second part of our discussion. All right. So to begin with, the first part will be about space science, and this is where we have to first understand what is the universe. Now, the very first thing when it comes to the universe, the understanding of the universe, it's very difficult to even understand or think how to define universe. If I ask you, how do you define universe? How do you define something that is undefinable, or something that has no beginning or no end or no boundary? How do you define that? So there is one definition that was given by one scientist almost 50 years back, and this is this: everything that exists, everything that has existed, and everything that will exist is a part of the universe. So this is how he basically tried to explain what the universe is, that because there is nothing beyond the universe. It's difficult to say that, okay, fine, this is the boundary of the universe and there are things that are beyond the universe. No, everything is a part of the universe. Correct. So everything, whether present, past, or future, is a part of the universe. And interestingly, we are talking about the past and the future as well. And we are not just saying that everything that exists is a part of the universe. No, we are saying that everything that exists, yes, everything that will exist, and everything that has existed, all these things are a part of the universe. Now, why do we say that? And how do I explain that? That past is also and future is also a part of the universe. There is a simple definition, simple explanation to it, and I'm very sure most of you have heard of it. Law of conservation of energy. What does it say? What is law of conservation of energy? Yeah, energy can neither be created nor destroyed. It can only be transformed from one form to another. Right? This is what we say. Law of conservation of energy. That energy can neither be created nor destroyed. It can only be transformed from one form to another. What do we mean? What do we mean by this? So what we are saying is that basically you cannot create energy, you cannot destroy energy, you can only change energy from one form to another. So now how does this explain the definition of the universe? So see, let's say there is a star, there is a new star that is formed today. Now this star comes into existence today, but it does not just come into existence from nowhere or from nothing. There are a bunch of gases or molecules, etc., that will come close together. They'll start forming a core, and hence they will start to form a star. Right? So there was something which got transformed into something else. And when, let's say, this star dies, so when the star dies, it will release some energy, release some particles, change into something else. So maybe change into a black hole, maybe change into a nebula, and so on. So it will just change its form. So everywhere in the universe, this is what's happening, that everything is just changing its form. So whatever it is today, tomorrow it's something else, but it came from what it was, and it will transform into something else. So that is basically how we are saying that universe basically becomes a bound system, that everything that exists, that has existed, and that will exist is a part of the universe. Now, in this particular scenario, when we talk about uh, the universe, this is where the complexity in the understanding of the universe begins. When we look at the composition of the universe, so when we are looking at the composition, there are three basic parts to this universe. What are the three parts? First part, dark energy. Second part, dark matter. And then the third part, the rest. So dark energy, we are saying that almost 70%, 68% to be exact. So almost 70% of the universe is nothing but dark energy. Almost 25% 27% to be exact, is nothing but dark matter, and then the rest has 5%. The rest has 5%. Now, what is dark energy and what is dark matter? Let us keep it aside for now. We'll discuss that. But first, let's focus on the rest. The rest is just 5%. And the rest is what we actually know of. The rest is what we actually see or observe. Out of this 5% also, 4% is nothing but just free hydrogen and helium. Just free hydrogen and helium. This makes up for 4% of the universe, which is pretty significant, right? In the context of the rest, which we actually know of, 4% is a big proportion. So 4% is hydrogen and helium, only hydrogen and helium. Coming to the last 1%, in the last 1% also, 0.5%, 0.5% is all the stars in the universe. All the stars, billions and billions and billions of stars in the universe, amounts for just 0.5% of the universe. How many do you see? 10, 20. If you're living in Delhi, 0. So all those stars that we see that only 0, that makes up for a very tiny fraction of the billions and billions of stars, and that makes only 0.5%. So 0.5% is all the stars in the universe. Then 0.3% is neutrinos. 0.3% is neutrinos. Now, what are neutrinos? Neutrinos are very special particles. Neutrinos are very special particles. These, I'll write it what exactly they are. They are chargeless and almost massless particles. All right, chargeless and almost massless particles. So chargeless meaning that they don't have a positive or a negative charge. For example, you might know that protons have positive charges, electrons have negative charges, neutrons have no charge. Similarly, neutrinos also, they do not have any charge. All right, neither positive nor negative. And almost massless particles. Why almost massless? Because their mass is a very tiny fraction. They are very light. They are so light that they are almost undetectable. It takes a lot of effort for the scientists to even detect a neutrino, something that has such a big presence. 0.3% of the universe is a big number in the context of what we know. So that's why neutrinos, these are chargeless and almost massless particles, and there are a lot of natural phenomena that lead to the formation of these neutrinos. So anything that is nuclear, for example, any nuclear reaction, nuclear fission reactions, nuclear fusion reactions, they can lead to the formation of neutrinos. Similarly, there is a phenomena called as supernova that we are going to discuss later. So supernova also leads to the formation of a lot of neutrinos. So that's why we know that there are a lot of natural phenomena that can lead to the formation of these neutrinos, which are just, you can say, spread around the space. They're spread all across the universe, everywhere. I mean, in your room right now, for example, there are a lot of neutrinos that you will never see, you will never detect, you will never observe. So similarly, all across the universe, there are a lot of these neutrinos that are just hanging around. So these are very special particles, very different kind of particles, which are called as, that's why, which are chargeless and almost massless particles. Now, and you might, if you read the news, you will see that India is also trying to build its own neutrino observatory. You might have come across this news, and if you not, you can just go and Google and you will find that India is trying to build its own neutrino observatory where we can detect these neutrinos. So we are building observatories to detect these neutrinos. So India is working on it. There are other neutrino observatories in the world. India is also building one right now. So but these are particles which you can't see, you can't detect. It's not easy. I mean, that's why I told you that right now in your room itself, through your room, a lot of neutrinos will just keep on hanging around, keep on passing, and you will never see them, you will never observe them, and they will not affect you at all right? So this is basically what neutrinos are. Then after neutrinos, you see that 0.17%, 0.17% are electromagnetic radiations and antimatter. Electromagnetic radiations like radio waves or the visible light, the sun rays, the ultraviolet light, the X rays, all these are electromagnetic radiations. We'll discuss more about electromagnetic radiations when we go to IT and communication chapter. Right now, just know that, okay, fine. In the universe, 0.17% is antimatter and electromagnetic radiations. Now, what is antimatter? What do we mean by antimatter? So, when we say antimatter, understand the meaning of antimatter, the term antimatter. Antimatter is any particle with same charge sorry same mass and opposite charge. Same mass and opposite charge. So basically they are called as antimatter. Now when we say antimatter, if I, let's say, ask you, for example, that if, let's say, I have electrons and protons, can I say that electrons and protons are antimatter of each other? Yes or no? Same mass, all right? Their masses are different. Masses are different because protons are almost 18-20 times, or let's say almost 2000 times heavier than electrons. So for antimatter, they have to have same mass and opposite charge. Here they have opposite charge, but they don't have the same mass, so that's why they are not antimatter of each other. Sorry. Antimatter of electrons are called as positrons. There are particles called as positrons. So these are antimatter of each other because they have same mass and opposite charge. All right, they have same mass and opposite charge. So that's why these two will be called as antimatter, whereas protons will not be called as antimatter of electrons. So you have to understand this, because see, these terms, why I am going to the details of these terms is because these are terms that you will see in your newspapers. So that's why just in one line know about them, just know the definition, just know one example, that will be enough for you, because these are too complex topics for UPSC to go into the detail. They are never going to ask you any detailed question on these kind of topics because these are very complex topics. So that's why just one line definition, one line explanation, one simple example, just know this much and that should be enough for your exam. All right, so that's why just understand why electrons and protons are not antimatter of each other, but electrons and positrons, they are antimatter of each other. Right? So we have free hydrogen and helium, stars, neutrinos, antimatter and electromagnetic radiation, and a small proportion, 0.03%, 0.03% of heavy elements. Now when we say heavy elements, here the definition of heavy elements is different. in general, your understanding of heavy elements would be that anything that has large atomic number or bigger atomic size, then in that case they should be called as heavy elements. But in case of space technology, that's not the case. When we say heavy elements, what we mean is every other element apart from hydrogen and helium. We already accounted for hydrogen and helium, correct? We have accounted for hydrogen and helium already, that 4% of the entire universe is nothing but just hydrogen and helium. Now we are talking about the rest. So that's why every element apart from hydrogen and helium, they are called as heavy elements. So now basically everything around you, everything that you see on the earth, everything around you, they are made of heavy elements. And this accounts for just imagine this accounts for just 0.03% of the entire universe. These heavy elements, I mean all the other elements apart from hydrogen and helium, they account for just 0.03%, which is a very 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 tiny fraction of everything, correct? So everything apart from hydrogen and helium, every other element apart from hydrogen and helium, they are called as heavy elements. So this basically is the breakdown of the composition of the rest, the 5%, right? This is what, this is just the 5%. Now coming to the problem, the rest 95%, which comes from dark energy and dark matter. So what do we mean by dark energy and what do we mean by dark matter? Let's try to understand that. But any question if you have until now, whatever we discussed in the last 15 odd minutes, in a very different context, we'll discuss that later. But just know that hydrogen with atomic number 1, that hydrogen we are talking about. Elements again, heavy elements example. So heavy elements example, every other element like oxygen, carbon, chlorine, bromine, uranium, all these are examples of heavy elements. So that's why every other element apart from hydrogen and helium, they will be called as heavy elements. Yes, like oxygen, correct. They exist in very large numbers and we have detected them, that's it. We haven't found any use for them. Doesn't really matter. 27 is the exact number. So, I mean, preferably if you can write 27. Please explain. Same mass and they have opposite charge. Electrons having a negative charge, unit negative charge, and positrons having a unit positive charge. Everything on the earth, everything that is organic, that is made of carbon, but beyond that, nothing. Is it atomic structure and everything? So there you will understand. So don't worry. Microdust, no. Less 1 and 2, I mean 1 electron in hydrogen and 2 electrons and 2 protons in helium, and that's why everything else has been classified as. Is carbon heavy element? Yes, it is. Contains 2 matter? No. It just depends on whatever antimatter, because it's just going to be opposite. So for electrons there are positrons, for neutrons there are anti-neutrons, so for protons also there are anti-protons. So just that mass will be same and charge will be opposite. And it is estimation of everything that has been observed and basically you can say an extrapolation of that. Example of it. Why is, move on. So now we know about the rest. We know that, okay, the 5% of the universe, what exactly it is composed of, we know that. Now coming to the 95% of the universe, where the bigger proportion is held by dark energy. As I told you, that 68% of the entire universe is said to be dark energy. Now, why do we call it as dark energy? What is the reason behind us calling it as dark energy? So is there, I mean, because of darkness or something, or maybe there are dark forces, there is a super villain that is driving this energy, so that's why it's dark energy? None of it. Basically when we say that it is dark energy, we are saying that it is dark energy mainly because we are in the darkness. We do not know what kind of energy it is. We have no idea. For us, this is an unknown form of energy. So that is why we are saying that it is dark energy. Now, if we are saying that it's an unknown form of energy, how do we even know that it exists? What are we basing this on? How do we know that, okay, there is something called as dark energy? To understand that, understand the formation, or rather the structure of the universe. So if you see this, this is how it is supposed to be. The structure of the universe, this is what the structure of universe is like. But it's not always the notion that we held. Initially, it was said to be that the universe basically is like this. The universe is flat. All right, the universe is flat, and it always has been like this. That the structure of the universe, whatever it is today, it was same yesterday, it was same lakhs of years ago, and it is going to be the same lakhs of years from now. This is what we used to say about the universe. The early understanding of the universe was this: that, for example, let's say there are three galaxies, A, B, and C. Suppose that these are three galaxies. So these galaxies, their relative positions will always remain the same, like this, because it's a fixed structure. The universe was said to be in a steady state. We used to call it as steady state, meaning that the structure of the universe does not change. Structure of the universe does not change. So this is what we used to think. All right, this is what we used to think, that the structure of the universe always remains the same. Then came a scientist whose name I'm very sure every one of you know, Albert Einstein. And Albert Einstein, he was working on his theory of relativity, and in his calculations he saw that according to his calculations, the universe should not be in a steady state, but rather it should be expanding. This was the conclusion from his calculations, that the universe should be expanding, it should not be in a steady state. But then he thought that he was wrong. So even Albert Einstein did not believe in himself, even he did not have the confidence in himself. So he thought that he was wrong, because he very strongly believed that the universe is in a steady state. So then he changed his equations in a manner that the universe again becomes static. So it's just like when you are solving a mathematics problem and you already know the answer, so you can write the steps. In class 8, 9, 10th, probably you have done this, that you already have memorized the answer. So somehow you just write the steps so that you can get to the answer. So that is what happened with Albert Einstein as well, that he thought that steady state theory was correct. So whatever equations he was getting, he changed it, so that the expansion of the universe, he didn't want to go and explain everyone how he thinks that the universe should be expanding. Then almost 10, 12 years later, another scientist, I'm sure maybe you have heard his name also, Edwin Hubble. The next scientist was Edwin Hubble. Now, Edwin Hubble, he also proved that the universe is expanding. He also proved that the universe is expanding. Then Albert Einstein also read the papers that was published by Edwin Hubble, and very famously, Albert Einstein said that this is the biggest blunder of my life. That this is said to be Einstein's biggest blunder. That he would have been the first one to explain that the universe is expanding, but unfortunately, after getting to the conclusions, he changed everything. Uh, so that's why the explanation does not go in his account. The explanation goes to Edwin Hubble. So Edwin Hubble basically explained the expansion of the universe. So he explained that universe is not in a steady state, but rather the universe is expanding. So now Hubble proved it. Later on, it was found that it's not only the fact that the universe is expanding, but rather the universe is expanding in an accelerated manner. All right. So initially it was Hubble who said that the universe is expanding. All right. He explained that the universe is expanding later, and by later I mean 1990s. So very late, because he had explained this in 1920s. I think 1928 it was, if I'm not wrong, when Edwin Hubble had explained this. So later it was found that the universe is not only expanding, but it is expanding in an accelerated manner. Expanding in an accelerated manner, meaning that there is an accelerated expansion of the universe. Now, what do we mean by accelerated expansion versus expansion? A normal expansion will be like this. All right. Just to give you the context, a normal expansion will be like this, and accelerated expansion will be like this. So this, I would say, is normal expansion happening in straight line, and this is what we would call as accelerated expansion, like a funnel. All right, this is basically the accelerated expansion. So if you see this, what you see is that this is an accelerated expansion, right? This is an accelerated expansion. So now, if this accelerated expansion is happening, there must be some kind of energy behind it. For any kind of work to happen, we need energy, right? That's clear. If you need to do something, you will eat something so that you have that energy to do that work. So here also, if expansion of the universe is happening, there must be some form of energy that is causing that expansion. This energy that is causing the expansion is called as dark energy. Now, why are we calling this as dark energy? Because we don't know what form of energy it is. We just know that there is some kind of energy that is leading to this accelerated expansion, but we don't know what kind of energy. We don't know what this energy is. We do not know the properties of this energy. So that's why we are calling it as dark energy, because we are in the darkness. We do not know what this energy is. So hence we named it as dark energy. So if you see this, what it basically is leading to is that, for example, let's say if these are three galaxies, let's say this is galaxy number 1, galaxy number 2, and galaxy number 3, then you can see that the distance between these galaxies is also increasing. Correct? The distance between these galaxies is also increasing. So it's not that the expansion is just happening at the edges of the universe, it is happening everywhere in the universe. So even the galaxies are moving apart from one another. So that's why in millions of years, the entire structure of the universe as compared to what it is today would be completely different. So it's not something that we would observe, because it's not happening so fast in the context of this large galaxy. So it's not something that you will be able to observe, but in millions of years, these are the things that will keep on happening. So that's why basically, uh, this is basically what we are looking at, that this is an energy that is leading to an accelerated expansion of the universe, an unknown form of energy. All right, an unknown form of energy which is hypothesized to permeate all of space, tending to accelerate the expansion of the universe. This is what dark energy is. All right, so what is dark energy in simple terms? The energy that leads to accelerated expansion of the universe, or rather the unknown form of energy that leads to accelerated expansion of the universe, is called as dark energy. All right, so this is how we define dark energy, and this is how we know that something like dark energy should exist. All right, so that's the first part, and it makes up, just imagine that this makes up for 68% of the universe. So almost 70% of the universe is nothing but dark energy. Now coming to the other unknown form, which is dark matter. Now, about dark matter, basically what we are saying is that this is an unknown form of matter, which again we know that it should exist because it shows in our calculations. We haven't seen them. We haven't seen any dark matter, but they should exist because it amounts for the calculations that we are doing. What do I mean? Just understand this. Let's say we see a galaxy. I'm using my telescope, and with this telescope, I am looking at a galaxy. And in this galaxy, I see a number of stars and number of planets, other celestial bodies, and so on. And all these movements, etc., that we are looking at, we observe something, right? And let's say our observation says that this galaxy weighs 1000 kg. But when we calculate according to these observations, when we do the calculations, our calculations show that this should not be just 1000 kg, but probably 5000 kg. But how is that possible? Because we have accounted for everything that we see. Just let's say, imagine your room. In your room, you are there, maybe your device wherever you are watching this lecture, maybe your notes, your pen, maybe your books, maybe bed, etc. in your room, uh, your study table, chair, whatever it is. So let's say you have taken everything individually and you have weighed everything, including the walls. You have taken the weight of the walls, etc., everything. And then you find that, okay, fine, this room is of 1000 kg. But then you pick up the entire room as a whole and you then weigh it, and you find that it is not 1000 kg, but it is 5000 kg. How do you explain that? There probably are unknown things in your room that are also sitting with you watching this lecture, probably, and trying to gain some information. Either that, or there is something which is completely unobservable, and hence that accounts for dark matter. So that you can see in a manner the ghost of the universe, where what we can't see, we cannot observe, but they exist. They exist because they amount for a huge amount of the weight or huge amount of the mass of the entire universe. That is what dark matter is. That every part of the galaxy, every galaxy and every part of every galaxy, they have dark matter, and they must have dark matter, otherwise we don't know how to account for all the unknown mass that we have calculated, all the unknown mass that we have calculated. So that is what dark matter is, that it is a mysterious non-luminous substance making up vast majority of matter in the universe. All right, vast majority of the matter in the universe. It does not interact with baryonic matter. Baryonic means every normal matter. Baryonic means normal, meaning electrons, protons, neutrons, etc. They are called as baryonic. All right, so they are called as baryonic. So it does not interact with electrons, protons, etc., and that's why it is completely invisible to us. So so that's why we say that this is what dark matter is, that it's an unknown form, something that we can't see, something that we can't observe, something that we don't know what it is. We just know that it must exist. Otherwise, all the calculations, we don't know how to account for those calculations. So that is basically how we are looking at dark matter and dark energy. So right now, for example, this mission is in news. Euclid mission. Have you heard of it? Even yesterday, or rather today, it was in the news. Heard of this? You have not? No issues. Euclid mission is a mission that was launched this year in July. July 2023, this mission was launched, and this is a mission of the European Space Agency. All right. This is a mission of the European Space Agency to explore the dark universe. The dark universe, basically, they are trying to find, basically, to find dark energy and dark matter. I'm sure that in tomorrow's newspaper you will hear about this. Look for this in tomorrow's newspaper. I'm sure that in tomorrow's newspaper, Euclid mission will be in the news, uh, because today, just today, they have captured some of the first pictures from this particular mission. The Euclid Space Telescope, which was launched in July, this basically has captured the first few images, and I'm sure that tomorrow all these images, for example, the horseshoe nebula, etc., they have captured all these images. So for the first time, these images have been published for the first time today. Yesterday it was in the news that very soon, or maybe within a day, the first images will be released, and today in the afternoon only they have released these pictures. So so that's why they basically are, look at the look at the time. I've just taken this newspaper clipping just before your class, because as soon as I saw it on my newspaper feed that finally the first pictures have come, I just brought it to your classroom. So as you can see, 1:37 p.m., so just hours before your class, these pictures were released. So I'm sure that tomorrow's newspaper will see this. So that's why for the first time there is a full-fledged mission. There have been certain missions like this before also, but this is the biggest such mission that has ever been taken to try and find dark energy and dark matter, or rather to understand dark energy and dark matter. All right. So that's why Euclid mission from this perspective becomes very, very crucial. Now, coming to the formation, but before formation, if you have any doubts, because I mean, these are a bit complex topics, that's why I'm asking you. If you say deep space, the meaning of the term deep space is when we are going beyond our solar system. So, for example, when you go beyond Uranus or Neptune, etc., then in that case, we say that these are deep space missions. Is dark energy a counterpart to gravity? Not really. There are some hypotheses about this, but we can't really say that because it's an independent energy altogether. But I know where you are coming from. But you have to understand that when we talk about gravity, we are talking about mass, because when you say that gravity is pulling the core of the universe, it is basically the mass of all these celestial bodies and the galaxies that are pulling everything together. But here we are talking about the expansion of the space itself. So it's not related to only the particles moving apart, but because of the fact that the space is itself expanding. Just imagine a balloon. Just imagine a balloon. Let's say that you have just marked 2 points on balloon, and when you start inflating the balloon, these points will start to move apart as the expansion of the balloon happens. So the space itself is expanding. So that's why saying that it is anti-gravity will not be entirely correct. Non-luminous means that something that uh, does not have light or does not respond to light, is not a source of light, let's say. 0.98. Achha, are you talking about this picture, is it? When example, air on the earth, we know that it is composed of uh, nitrogen in very big proportion, then after that oxygen, and then all the other gases like carbon dioxide, etc. So we know about air, so we are not talking about air here. When we say dark matter, it's completely unknown. We don't even know what it is. We just know that there should be something. We do not know what. All right, but air, we know the composition. And second is just something that exists everywhere, but we don't know what it is. Explanation could be completely different from what right now our way of thinking is. Beyond our solar system. Due to dark matter, yes, that's correct. When we say dark energy, we are saying that this is the energy behind the expansion of the universe. All right. The energy that is working in expanding the universe is called as dark energy. What is dark matter? It is just the matter which is found everywhere, which should be present everywhere, but we don't know what kind of matter it is. We just know that there's something, there should be something, because there is a large amount of unaccounted for mass that we are seeing in front of us 100 kg, but we are calculating 500 kg. So that 400 kg, where is it coming from? Maybe from dark matter. So that's why that unknown matter is dark matter, and the energy behind expansion of the universe is dark energy. So they're completely different concepts. Exact picture, uh, capture certain rays, they capture certain radiations, and they process those radiations to an equivalent of how it would look. Basically, purposes. Euclid mission is important. Canaveral meaning Cape Canaveral is the place from where the launches are done. It is hard to understand or imagine. Understand this. See, basically, let's say that through your telescope you are looking at a galaxy. All right, you're looking at a galaxy, and you found that there are 5 suns there. You found that there are 10 planets there. You found there are certain other things. So you found all these things and you calculated that, okay, fine, these are the things that I see, and whatever you see in front of you, you calculated all together that to be, let's say, 1000 kg, whatever you saw. But then you observe the motions, the forces that are working there, the gravitational pull of each and everything. And when you do that calculation based on that, then you realize that whatever you are seeing is not really correct, because then your calculation based on all the forces and all the movements that you are seeing, based on that you see that it should be something else. So that difference between what we see and what we calculate is dark matter. Electromagnetic radiations plus other forces that they will be working for or working on to uh, understand whether it's a possibility. So let's look at that. Break. Let me take some 10 more minutes. After this topic, we'll take a break. Edwin, shift, the observation of all the related phenomena. These are the things on which their observations were based upon. Expand all these XYZ things, they exist. Hydrogen, helium, all these things also exist. Now, coming to how was the universe formed? Where did the universe come from? So, to explain that as well, there are various theories, out of which the most widely accepted theory is the Big Bang theory. The Big Bang theory is the most widely accepted theory about the formation of the universe. All right. But apart from that, we know that there was steady state theory, which has been discarded now. Then there is the eternal inflation theory. Eternal inflation theory talks about a very popular topic of the films and TV shows, etc., the multiverse. Multiverse, meaning that there are multiple universes. This theory says that there are multiple universes, and our universe is one of those multiple universes in which we belong. So, I mean, in the films, etc., you might have seen this a lot of times, but in reality, it has never been proved to be correct. Then there is the oscillating universe theory, which says that the universe keeps on contracting and expanding. That right now there is an expansion in the universe, but then there will be a time when again contraction will happen in the universe, and then again expansion will happen, and this is a cycle that keeps continuing. So this is what oscillating universe theory says. String theory and big bounce are, I would say, a little more important, and we'll discuss about them. So these three, the Big Bang theory, the string theory, and the big bounce theory, these are three theories which sometimes will be in the news, and they are important because especially when it comes to the Big Bang theory, this is the most widely accepted. This is the most widely accepted theory. Most widely accepted theory, the Big Bang theory. Now, what exactly does the Big Bang say? What is the Big Bang theory saying? The Big Bang theory says that the universe was very hot and concentrated in the distant past, and ever since then, the space has been stretching and cooling. So, what it says is that in the distant past, the entire universe, just remember this, the entire universe would have been just a very tiny particle, a particle which would have been even smaller than the size of a proton, even smaller than a proton, such a small particle. And all the forces, all the matter, everything that we have in this giant universe today, all these things were there inside this tiny particle. Now, in this tiny particle, all of a sudden expansion started. And this is where once the expansion started, this is where all the matter, all the forces, all the energy, they started to have their independent existence. Before this, we say that in a manner, this entire universe was like a soup. This entire universe was like a soup, just like how you have, let's say, if you have a veg soup, then you have all the different types of vegetables, etc., which is just mixed there in that soup. So something similar was the case of the universe when it began. And then expansion started here, and as the expansion started, all these particles, forces, matter, etc., they started to exist independently. All right. So this is basically what the Big Bang theory says, that in the distant past, the distant past means 13.8 billion light years ago. So in the distant past, the entire universe was nothing but a very tiny particle. And then expansion started in this particle in a manner that it came to the present scenario in all these years. So this is what the Big Bang theory says. Now, when we talk about the Big Bang theory, why it becomes the most widely accepted theory is mainly because how it has been, whatever explanation it had given or whatever predictions it had made about the universe, about the origin of the universe, everything was found to be correct later. So that's why it became very widely accepted, that it's not just based on a hypothesis that there are multiple universes and we are just a part of one of those universes. It's not based on some assumptions. Whatever it said, whatever this theory said, all those things were proved to be correct. So that's why there are evidences that support the Big Bang theory. All right, there are evidences that support the Big Bang theory. So there are three basic evidences. Just try to understand these evidences. First is Hubble expansion. So Hubble expansion is nothing but the accelerated expansion of the universe. Accelerated expansion of the universe. So we discussed this anyway. We know that the universe is expanding in an accelerated manner. So that accelerated expansion of the universe is called as Hubble expansion. Then after that, cosmic microwave background. Let's hold on to this concept. The third is Big Bang nucleosynthesis. Big Bang nucleosynthesis is nothing but the abundance of hydrogen and helium. And we discussed about this as well, that 4% of the entire universe is just hydrogen and helium. So this abundance of hydrogen and helium is also explained by the Big Bang theory. So that's why these two evidences, and the third evidence is cosmic microwave background. So understand this term, cosmic microwave background. First word is cosmic. What is cosmic? Anyone? What is cosmic? What is the meaning of cosmic? The space is called as cosmic, right? Correct. Now, microwave. What do we mean by microwave? We want. So, because it is related to heating. So, this is a kind of electromagnetic radiation which is related to heat. So, cosmic microwave background, meaning that in the background, we are looking at microwaves, cosmic microwaves, meaning that microwaves which are in the space. That's why cosmic microwave background. Now, these three images that you see right here, the three images that you see, these are the three images which are related to the cosmic microwave background. There have been 3 different missions. The first mission was called as COBE, COBE. This was in 1993. Then there was the second mission called as WMAP. This was in 2006. And then there was the third mission called as Planck. I think this was 2009. So if you see, this basically is the image of the cosmic microwave background, something like this. If you look at this, basically what it shows is that WMAP is looking at the outer universe. It's just like you sitting with your telescope, that you go to any rooftop and there you just sit with a telescope and you're watching the night sky. All right, you're just watching the night sky from this end, and while you see all these stars and planets and all the celestial bodies, etc., in the background, sorry, in the background, you see or you observe microwaves. So this is what I'm talking about, that in the background, through these kind of telescopes or these kind of instruments like WMAP or Planck or COBE, etc., we see that in the background microwaves are visible. What does the microwave signify? The microwave signifies the amount of heat that was present in the early part of the universe. In the early universe, we are saying that the universe was hot and concentrated, right? This is where we begin from. The universe was very hot. Very hot meaning it is estimated that the temperatures would have been 10 to the power of 32 degrees Celsius. 10 to the power of 32 degrees Celsius would have been the temperature of the universe. So that's why we are saying very hot and concentrated. So that's why in the background, through these kind of instruments, when we see in the background, these microwaves are visible. So just remember that these microwaves, I'm just writing it here, microwaves signify extreme amount of heat present in the early universe. All right, so this is cosmic microwave background. So that is basically what the cosmic microwave background signifies, and that's why it has been a very, very important concept. Every now and then, I mean, you can say once or twice a year, you'll find the mention of cosmic microwave background in some article in the Hindu or the Indian Express. So that's why as a topic it is very important. Nobel Prize just a couple of years back, the Nobel Prize in physics was also given to something which was related to the discovery of cosmic microwave background. So that's why cosmic microwave background as a concept is a pretty important concept. All right, so just understand what is cosmic microwave background. A background of microwaves that we see. As you can see, it is what? It is in the background, that I'm seeing it from this side. And when I'm looking at the universe, I see all these celestial bodies. And in the background, right, at the far side, I'm looking at microwaves. So those microwaves, they signify that there was a lot of heat present in the early part of the universe. All right. So that's why cosmic microwave background becomes a very strong uh, evidence that supports the presence, or that supports the Big Bang theory. Understood? So this is basically what it is. Now there are still questions that are unanswered. For example, what before the Big Bang and what caused the Big Bang? So what before the Big Bang and what caused the Big Bang are two questions which we still haven't been able to answer. All right, so we are saying that there was this particle, but what before this particle? Where did this particle come from? It does not say anything about that. It just talks about that particle being present. And that what caused the Big Bang? We are saying that there was a sudden expansion, but where did this sudden expansion happen from? What led to, what was the trigger for this sudden expansion? We still don't know. So that's why we still say that there are these questions which are still unanswered by the Big Bang theory. And that's why remember that this is a theory. It's not a law. It is not like the Newton's laws of motion that they are universal, or they are not like laws of gravitation that they are universal. They are still what they are, theories. This is the Big Bang theory. Tomorrow somebody might come and they completely might destroy this theory, saying that this is completely wrong, and they might come out with a completely new theory. So then after that, all these classes will be vain, right? All these classes will be of no use. So uh, so that's why these, just remember that it's still a theory. So let's take a break here. We'll uh, first thing, we do not call it as an explosion. All right. Be very careful here that whenever we are saying, we are talking about the term expansion. All right. So we are saying that there was an expansion that started in the universe, which was a very sudden expansion, but we don't call it as explosion. Although, if you go to various resources on the internet, you will see that very often somebody or the other calls it as an explosion. But exactly calling it as an explosion will be wrong. All right. So that's why be very careful when you use these terms. Please try to use the term expansion whenever you do, and not the term explosion. All right. Secondly, when we talk about this dark energy, we say that whatever stretching of the universe has been happening, it's all dark energy. But the initial expansion wouldn't have been dark energy. Initial expansion was very different, because everything was just coming into its existence. So at that point of time, calling it as dark energy would not be entirely correct. But just, you can say, minutes after the formation, almost, you can say, almost after 20 minutes, you can say after the first 20 minutes after the formation of the universe, this is where we can say that dark energy in a manner started taking its form. Eternal inflation theory. Eternal inflation theory, see, in these kind, uh, two of you have asked almost a similar question, Tehseen and Vivek. So see, multiverse with diagrams, I mean, every diagram will be an imaginary diagram, because we are saying that these are just theories where we do not find any hard scientific background, right? In case of Big Bang theory, there is a hard scientific background on which it is based. Multiverse theory or the eternal inflation theory is not based on that. So that's why we cannot really say that it's there something. We are just saying that it says that there is a huge multiverse in which there are very many small universes that exist. This singularity is less than size of a nail. Forget about size of nail. We are saying that it is smaller than the size of a proton. So not only a nail, but a size smaller than size of proton, which is millions of uh, meters of diameter lesser. Please explain the concept of ghost matter and its link with dark matter and dark energy. So exactly when we say ghost matter, I mean, these are very rough words that are used, often used for neutrinos more than dark energy or dark matter. Rough diagram, I mean, for multiverse theory, we say that it is something like this, that there are multiple universes that lie inside this multiverse. I can neither confirm nor deny this. These theories, these and a lot of different concepts that existed, and everything just being taken together. Concepts that we have discussed until now, and then the basics of the formation of the universe, the basics of Big Bang. Are there any evidences of multiverse theory? No, there isn't. What after the expansion of the universe started, the first particle to come into existence, we say, would have been quarks. All right, and these quarks then further might have led to the formation of hadrons and leptons. Hadrons and leptons. And these hadrons further would have led to the formation of protons and neutrons. And leptons, we say, that might have led to the formation of three particles: electrons, muons, and taus, TAU. All right, and this is where protons and electrons would have come together along with neutrons to form the first atom, which would have been hydrogen. And this hydrogen further led to the formation with nuclear fusion. With nuclear fusion, led to the formation of helium. So the formation of hydrogen and helium, it began very quickly. All right, it began very quickly just after the formation of the universe, and almost for the next 380,000 years, only hydrogen and helium were being formed. So for 380,000 years, only hydrogen and helium. And then after that, we see that other gases, etc., they also start coming into existence. So that is the reason why we see that the amount of hydrogen and helium in the universe is much more as compared to any other element. Particle that came into existence. Understanding the origin of everything that exists is where basically all these things matter. Why is of the spin all these divisions are done, but I really can't go there. That's way beyond what we need to learn. Discovered as we can't see it. Basically, it is based on our basic understanding of matter and what we believe is could be true, and experiments are done based on that. Many instruments, microscopes, etc., are used to understand that. Top believed to be correct, and there is a certain kind of explanation that string theory comes with, which probably can explain few things which are not explained by the Big Bang. So that is why string theory becomes important. That is the reason why there is a lot of research happening here, a lot of new studies, and there are a lot of new experiments that are being done in the field of string theory. Now, what does the string theory say? String theory says that every energy, every particle that we know of, every force that we know of, they are all made of tiny strings. All right. They say that they are all made of tiny strings, and various types of vibrations in these strings, they make different particles. Very difficult to even think of that what they're saying. They're saying that if the entire structure of the universe that we know of is just like how the musical notes are uh, produced out of a guitar or a sitar or any stringed musical instrument. That, for example, if you have a guitar, then you will see that every string that you have in that guitar can produce a different note. Wherever you are plucking the string will also produce a different musical note, and a combination of all these things will make the music, right? So it says that the entire universe is also something similar, that the entire universe is made of very tiny strings, and various vibrations in these strings will produce different kinds of particles. So one kind of vibration will produce one kind of particle, another kind of vibration will produce another kind of particle. So this is what the string theory says. This is what the string theory is saying. So that's why string theory from that perspective basically tries to define the existence of each and every matter and force, etc., in a very different manner, as compared to whatever we whatever explanations have been fed to us until now through the Big Bang theory or some other theories like this. So that's why string theory becomes a completely different way of explaining the universe. So it describes the fundamental level of the universe in terms of vibrating strings rather than particles. So it says that everything is made of these tiny strings. So why so, and why exactly are we so much bothered about trying to prove string theory correct? And this is something which is related to something called as theory of everything. Theory of everything. Now, what theory of everything basically says is that there should be a possibility, there should be a way to unify all the fundamental forces. Just hang around for a bit. I'll explain everything that I'm saying. I know that these things might seem to be very difficult, but just give me some 5-10 minutes. Let me just unfurl everything. So So first and foremost, theory of everything. What does theory of everything say? Theory of everything says that there should be a possibility that we can unify all the fundamental forces. The first and foremost, what do we mean by fundamental forces? We are saying that there are four fundamental forces. What is this? So Somu, you are already correct. What are fundamental forces? So there are four forces that we call as fundamental. What are these? One is strong nuclear force. One is weak nuclear force. One is electromagnetic force. And then there is the gravitational force. So these four forces, they are called as fundamental forces. Why fundamental forces? Because these are the four forces on which every other force is based upon. So any other force that you know of, any other mode of force that you know of, is either one of these four. All right. So these four are called as fundamental forces. Now, they are also called as fundamental forces because we say that these are completely different types of forces, and we do not know how to convert one into another. They are independent of each other. So for example, electromagnetic force, so electrical charge, magnetic force, etc. Right? So electricity works on it. The poles of the earth or poles of a magnet, etc., they are based on the electromagnetic force, and they have nothing to do with gravitation. They have nothing to do with gravitation. So these are called as fundamental because all of these four forces, they are independent of each other. But theory of everything says that there must be a possibility that we can unify all these four forces through one single theory, or maybe through one single equation. Because when the universe started, it was all a single particle, right? There was one single small particle, and all these forces were unified. All the particles were unified. All the forms of energy were unified. So if they were unified in the past, there must be a way to unify them again. This is basically what the theory of everything says. So that's why theory of everything basically say tries to, this is basically about unification of the fundamental forces. This is about the unification of the fundamental forces, that all the four forces can be unified as one. And that is possible only if the string theory can be proved to be correct. Because we are saying that everything is coming from one single string, very, very tiny strings and vibrations in these strings. So, so that is basically why string theory becomes famous, you can say. Hasn't been proved to be correct yet. A lot of studies happening, a lot of experiments happening, but haven't been proved to be correct. So what it says is that every particle or force is made of very tiny vibrating strings, right? Very tiny vibrating strings. So various vibrations, various or rather different vibrations different vibrations in these tiny strings produce various particles or forces. So this is what the string theory says. All right, this is what the string theory says. So basically that's why string theory becomes famous, because it might be the theory that proves theory of everything to be correct. Now there is one small concept, another small concept here, which is called as the standard model. Standard model of physics, because very often again this is something that sometimes will be seen in the newspapers. So standard model of physics. So standard model of physics is where we include the strong nuclear force, the weak nuclear force, and the electromagnetic force. When only these three are considered, it is called as the standard model of physics. Gravitational force is a very weak force. In terms of magnitude, strong nuclear force is the strongest of all of them. Then comes the electromagnetic force, then comes the weak nuclear force, and then comes the gravitational force. So in terms of magnitude, gravitational force is very, very weak as compared to all the others. And that's why gravitational force is excluded out of the standard model of physics. Why standard? What is standard? Don't worry about that. Just know this much, it's enough. So look at this question. This question was asked in your paper 2017. Those string theory we just read about and standard model we just understood, sometimes seen in the news in the context of what? Observation and understanding of the universe. That is what we are looking at. That string theory tries another explanation for everything that exists in the universe. Study of solar and lunar eclipses, nothing to do with just the eclipses. Placing satellites in the orbit, again, nothing related to just the satellites. Origin and evolution of living organisms. It's not only about living organisms, it's about everything in the entire universe, right? So that's why the correct answer will be A. So so after really going through everything and all the complexities in the last 1.5 hours, this is what the question has been. All right, that's the level of question that they have asked. That if you have just heard the terms, you'll be able to answer the question, right? So universe, the formation of the universe, the various theories trying to explain the universe. Now we come to the celestial bodies. Now in the celestial bodies, the first and the foremost, the most important celestial body is a star. Now star basically is any celestial body that generates light, and rather you can say heat and light by nuclear reactions, and is held by its own gravity, and has, you can say, almost a spherical shape because of gravity. So I'm just adding it here. Has spherical shape due to gravity, because basically what happens is that gravity will try to pull everything towards the center, and it gives it more or less a spherical shape. So that's why stars are said to be spherical, because of gravitational force. So heat and light by nuclear reactions. What kind of nuclear reactions? Nuclear fusion reactions. What is nuclear fusion, etc.? We'll discuss that later, don't worry. So this is what a star is. And in the universe, we know that there are multiple stars. There are billions and billions and billions of stars that we have in the universe. How does the formation of of a star happen? It starts with a nebula. The stars will originate from a nebula. Now, what is nebula? The figure that you see right here on your screen, this is the figure of a nebula. Another figure that we saw of the Euclid telescope, the picture taken by the Euclid telescope, that's also a nebula. What is a nebula? The most widely used screensavers and wallpapers in the world, right? There was a survey that was done that found that nebula is the most common of all the wallpapers and screensavers that's used by people across the world. But fine, uh, that's another story. But when it comes to nebula, what is nebula? You can see that these are very beautiful pictures like these, and these are nothing but regions in space of dust, gases, etc., where a lot of dust particles, a lot of gases like hydrogen, helium, even ammonia, carbon dioxide, etc., they'll start to gather together along with some dust particles, etc., also. And then what then happens is that maybe it forms a region of especially hydrogen, where fusion of hydrogen begins. And if fusion of hydrogen begins, this is where a ball of mass will start forming, hydrogen and helium. So a ball of mass will be formed. So then it will have a mass. So because it has mass, it will have gravitational force. So it will now start pulling everything in the surrounding areas towards itself and starts to become bigger. All right, starts to become bigger, and this is where it is called as a small star or a protostar. So from the nebula, so what is nebula? Nebula is region of gases and dust in space. All right, region of gases and dust in space. Now, in this particular case, what we see is that from nebula, a small ball of mass like a star will be formed. It will start getting bigger and bigger and bigger. And ultimately, we'll see that because of the gravitational force, it will get its spherical shape and it will start forming a ball of mass. And then nuclear reactions will begin in this ball of mass at the center. And this is where we see that it ultimately converts into a star. All right, it will ultimately convert into a star. So this is how the formation of a star happens. Now, when we look at after the formation of the star, so from a nebula, formation of a star has happened. Now let me ask you a question. I'm sure that you've heard about the term black hole. So let's say if my question is, when our sun dies, let's say UPSC has given you this one statement: it will convert into a black hole. I'm launching the poll also for you. A for yes, you have very clearly. So what we know is that black holes are formed when a star collapses or when a star dies. But does it mean that when every star dies, a black hole will be formed? The answer is no. There are two types of stars which will be formed after a nebula. Either you will have an average star or you will have a massive star. So average star is any star that has mass up to 1.44 times the mass of our sun. All right. So average star, stars with mass up to 1.44 times mass of the sun. All right, these are called as average stars, and anything beyond that, everything that has a mass beyond up to 1.44 times will be called as the massive star. All right, so for example, let's say if the sun is of 100 grams, just consider for a moment that if our sun is of 100 grams, then up to 144 grams every star will be called as an average star, and beyond 144 grams all the stars will be called as a massive star. So our sun included, our sun will also be called as an average star. So average star, when it starts to die, first it converts into a red giant. All right. First it converts into a red giant. From there on, it converts into a nebula, planetary nebula. Nothing to do with planets. Unfortunate naming, but what can I do? So it does not mean that it forms a planet or something like that, just that its structure is a disc shaped structure, so the scientists gave it a name as planetary nebula. They should not have. They don't know that there are a lot of non-science background students also who are going to learn about planetary nebula. So so planetary nebula, the name has been given just because it has a shape like a planet, so nothing to do with a formation of a planet or anything like that. So planetary nebula, and ultimately it will form a white dwarf. So that's why when the sun dies, it will convert into a white dwarf. All right, it will, no, so that's because it will convert into a white dwarf. Now, for a massive star, what we see is that when they die, they first might convert into a red supergiant, very big sized, with star with very low temperature, red supergiant. And then from there on, supernova will happen. So supernova is nothing but basically an explosion, or I'll write massive explosion. Massive explosion at the center of red supergiant. Massive explosion at the center of red supergiant, and just remember that they are the biggest source sorry, source of neutrinos in the universe. So supernova will happen. So supernova is nothing but an explosion, because this red supergiant now becomes very unstable, very highly unstable, and an explosion happens at the center of this red supergiant, and this explosion basically will be called as supernova. And then after this explosion, either a neutron star will be formed or a black hole will be formed. So even here, there's no guarantee. There's no guarantee that when a massive star dies, it will always convert into a black hole. There's no guarantee of it. It can convert into a black hole. It might convert into a neutron star. So, and when neutron star will be formed and when black hole will be formed, there is no clear demarcation here, that what are the specific conditions under which a black hole might be formed or a neutron star may be formed. Both can be formed here. So either one or the two. Neutron stars are very small size stars. All right, the smallest stars, you can say. Neutron stars, basically these are the smallest stars. Remember, I'll this 1.44 times is also called as Chandrasekhar limit. If you have heard of this term, Chandrasekhar limit, because he was the one who proved it, that if a star has mass up to 1.44 times the mass of the sun, then in that case it will convert into a white dwarf, and white dwarf only, and only above this there is a possibility that they might form a black hole. Below this, no. So he was the one, and that's why this number 1.44 has been named as Chandrasekhar limit, because he was the one who proposed this theory, or rather he proved it to be correct. So that's why the number was named after him. How it will have no 5 lakh in the black holes. So why we are saying that it is a black hole? The term black is being used because this signifies absence of light. All right, this black signifies absence of light. Signifies absence of light. So that's why black, because this is a region, a black hole is a region where even the light particles cannot escape the black hole or the strong gravitational pull of the black hole. So that's why what happens is that, let's say if it is a black hole, light particles which are passing by, they will fall into the black hole, to the center of the black hole, and that's why uh, it will signify the absence of light. So that is basically what happens when it comes to a black hole. So that's why black hole, because you can imagine this like a well. Just imagine a well. So you might see that a well also has a boundary all across it, and if you cross that boundary, I'll suggest against it, but if you cross that boundary, what happens? You fall into the well. Same happens with a black hole as well, that in a black hole there is a boundary which is called as event horizon. We saw this term here, event horizon. So event horizon basically is the boundary of this black hole, and if anything crosses that boundary of the black hole, then in that case it will fall into the black hole. So as long as you have not crossed the boundary of that black hole or the event horizon, you are safe, you're not going to fall into it. Same goes for any particle, any matter, light, particles, etc. as well. Anything that has not crossed the event horizon will not fall into the black hole. So that is why hole is the term that we are using, that it's like a hole, it's like a well, and it pulls everything towards its center. Its center has a very, very, very strong gravitational pull. It has a very strong gravitational pull, and that's why anything that has mass in the vicinity will fall into the black hole, will be pulled by the black hole. So that is basically what we say in cases of black hole. So what we are saying is that these are places in space where the pulling force of gravity is so strong that even the light cannot escape. All right, even light cannot escape, even light particles, because light is also made of light particles or photons as we call them. So they will be uh, pulled by the black hole, by the gravitational pull of the black hole, and hence this is happening. So this is basically a very, very, very strong gravitational center, a very strong gravitational center. Otherwise, what we just also discussed is that gravitational force is a very weak force. So that's why there what happens is that at a very tiny space there's a lot of mass. In a very tiny space there is a lot of mass. So just imagine the entire mass of a massive star, the entire mass of a very, very big giant star now is concentrated at a very small place, and that's why the gravitational pull of the entire star is there in this one single point. So that is why black hole basically becomes very strong in this particular case. So if you see this, it's something like this, that you have this event horizon which is like the boundary, right? So event horizon basically is the boundary. So uh, any crosses the event horizon or the boundary of the black hole will fall towards the center of the black hole. And the center of the black hole is called as singularity. So as you see here, this point is called as singularity. So singularity is what? Singularity is the center of the black hole. Wait, I'll write in another color. I'm not sure whether it is visible. Right? So basically, this is what is happening. That until this point, until any particle has reached the event horizon, they still have a chance that they'll be able to escape the black hole. But once they cross the event horizon towards the center, they'll simply fall into the center of the black hole. So that is what event horizon and singularity in case of black hole, that is what the significance of these two topics or these two words are. So basically this is what black hole is. Now there is one more term here which is called as gravitational waves. Now gravitational wave, as the term itself suggests, this is a term that is related to a kind of wave that is being produced because of gravitation, and it is something that was first predicted by Albert Einstein. Albert Einstein had predicted it almost 100 years back. 1914, 1915 is when he had predicted it. And after that, it took us 100 years to prove that his predictions were actually correct. So that's why, that almost a century ago, he figured out uh, gravitational waves, and uh, there was no computer. Obviously, there was no computer back then. And then with all the technologies that we have today, we finally were able to prove the existence of gravitational wave. And the detection of gravitational wave, the first detection that happened, after that even the Nobel Prize was given for the detection of gravitational wave. Now, so this is what I mean. If you remember, we discussed about major scientific breakthroughs and running stories in the field of science. Gravitational waves have been in the news, I mean, have been in discussion for the last 100 years, because prediction happened in 1915, and then 2011, I think, was when, or 2010, it was when the detection happened. And then Nobel Prize was given, I think, in 2014. I think in 2014, the Nobel Prize for detection of gravitational wave was given. Until 2013, how many questions were asked from gravitational waves? The answer is zero. 2014 onwards, until now, there are one, two, three that I remember. There are at least three questions in the last 10 years based on gravitational waves. So that is what I mean. That when something becomes a major scientific breakthrough or a running story, then a question comes from there. UPSC examinations are being conducted for almost forever, but the question was never asked on gravitational wave. Question was asked after Nobel Prize was given, after the existence was proved to be correct. Before that, it was just nothing but a theory. So what is gravitational wave? Let's try to understand this. So gravitational waves are waves which are being caused because of gravitational force in the entire universe. Now, how do we explain this? Look at this. When we think of the structure of the space, we think of it like a net, like a mesh. Just imagine a football goalpost. Just think of a football goalpost. Now, what do we see at a football goalpost? That if, let's say, somebody, sorry, let somebody uh, kicks football towards the goalpost, what happens? As soon as the football hits the net, there will be waves that will be produced out of the net. Correct? How violent these waves will be depends on what is the mass of that football. So, for example, let's say instead of a football, I take a very small stone and I throw that stone towards the net. What will happen? Even if it hits the net, waves will not be produced, or even if waves are produced, very small waves will be produced. On the other hand, let's say I have a football which is made of iron, and this football made of iron is what I kick towards the football goalpost. What happens next? First, I break my leg, but then when this football hits the goalpost, very violent waves will be produced. Correct? So, depending on the mass of the football that is being hit towards this goalpost, the waves will be generated. Something similar happens in the universe as well. There are uh, there are a lot of phenomena, or you can say like a lot of events which are very highly energetic, which are very high mass. So for example, even the formation of black hole, or sometimes merger of black holes, merger of galaxies, collision of stars, these collision of galaxies, these kind of events happen, and these are really very violent events in the context of our universe. So whenever these kind of events happen, they will put a huge dent in this mesh of the universe that you have, and that's why waves will be produced from here, waves which are gravitational in nature. Why? Because there are large masses that are involved. So that's why waves will be produced from here. Will earth also produce gravitational wave? The answer is yes, but it will be negligible, because in the context of the universe, earth has a very insignificant mass. All right, earth has a very insignificant mass, so that's why can't consider the earth. So that's what's happening here. All right, that's what's happening here, and that's why this is what happens. So it is caused due to violent and energetic events like colliding black holes, supernova, collision of neutron stars, etc., or anything like, as I said, collision of galaxies, collision of stars, merger of black holes. All these kind of events, they can lead to the formation of gravitational waves. For the first time, the detection of the gravitational wave was done by the instrument called as Laser Interferometer Gravitational Wave Observatory, or LIGO. So this was the instrument, the picture that you see right here. This was the instrument that for the first time took was able to detect the gravitational wave. So that's why this becomes very, very important. And India is also developing gravitational wave observatory. India is also developing gravitational wave observatory called as Indigo LIGO. So the name that has been given is Indigo LIGO. So now Indigo LIGO is something that we are building, and very recently, although this was announced almost, I think 2016 it was, or 2017, when India has announced that India will also be making its own gravitational wave observatory with the help of LIGO. So India announced it, but very recently, just a few months back, in the month of May 2023, May 2023, finally, budget has been allocated. Budget allocation has finally been done for the Indigo LIGO project that India is working on. So that's why now this is a step forward. Announcement had happened long time back, but now we see that there's a step forward here, that now budget allocation has been given, has been done, and India is also moving forward with its own gravitational wave observatory. And merger of giant black holes. Merger of giant black holes billions of light years away from the Earth. What is the significance of this observation? Now, this observation happened in December 2018. This was news of December 2018. And just remember this, that this news was not there in the Hindu. It was there in Hindustan Times. I think it was there in Indian Express as well, but not in the Hindu. So then you would say that it is an out of syllabus question, because it's not a static question, and even in the Hindu it's not there. But we have a keyword here, a key phrase rather, I would say. And the key phrase is merger of giant black holes. What happens when merger of giant black holes happen? Without fail, gravitational waves will be generated. No doubt about that. Whenever you have any scenario where you have something so energetic, so violent, so massive, gravitational waves will be generated from here. All right. So what is the significance of this observation? Higgs boson particles were detected. Now Higgs boson is related to very small tiny particles, so force particles, so nothing to related to black holes. Gravitational waves were detected. Possible? Possibility of intergalactic space travel through wormhole was confirmed. This was only confirmed in films like Interstellar, etc. Has never been confirmed in real life. So that's why this is wrong. And enabled the scientists to understand singularity. Now we already have a basic understanding of singularity. I know where the confusion comes from. You know that black hole has a singularity, the center is singularity. So you see black hole, you see singularity, and you think that probably this is the correct answer. But understanding of singularity is something that we already have. So that is why the correct answer actually here will be B. Gravitational waves are detected. Just remember that whenever merger of giant black holes happen, merger of stars happen, collision of stars happen, formation of black holes happen, any of such events will always lead to generation of gravitational waves. And that's what happened here as well. So that's why these kind of current events or current affairs based questions also can be answered if your thought process is aligned correctly. If you are able to think in the correct manner, many a times you will see that even news based questions can be answered from your static knowledge, even if you have not read the newspaper, even if you have not read or come across that uh, article or that news. Now this will be the last topic for us today. This is about the sun. So we know that the sun is the center of our solar system, the entire solar system where we belong. It all hangs around this particular sun. So which is a star basically, right? This is an average star, which is also called as main sequence star. Just know this from prelims perspective, that the average stars generally they are called as the main sequence stars. Now, in this particular scenario, when it comes to the sun, the structure of the sun, first of all, how exactly is do we look at the sun? First and foremost, you have the core is where the nuclear fusion reactions occur. So nuclear fusion reactions, they take place here. So obviously the temperature at the core of the sun is pretty high, right? Temperature at the core of the sun is very high, because nuclear fusion is happening here. A lot of energy is being generated, a lot of heat and light is being generated. So temperatures are pretty high. The, the temperature can be in the range of 15 to 20 million degrees Celsius. All right, 15 to 20 million degrees Celsius could be the temperature of the core. So all the heat, all the light is being generated from here, and then it starts to go outward, right? From the core, it goes outward. So you have radiative and the convective zones that help in the uh, sending of these energy and the heat particles, etc., towards the outer part of the sun. The outermost part of the sun, the surface of the sun, is called as photosphere. So photosphere basically is nothing but the surface of the sun. This is the surface of the sun. The temperature here drops drastically now because we have come very far away from the energy generation core, right? So surface of the sun will have a temperature of almost about 5500 degrees Celsius. 5500 degrees Celsius will be the temperature of the core of the sun, right? Now from here on we have chromosphere and corona. Now chromosphere and corona, they together they make up the atmosphere of the sun. They make up the atmosphere of the sun. So this is basically the part that is often visible during the solar eclipse. So during a total solar eclipse, you might see that there is a thin ring-like structure that is visible. Have you seen the pictures? Have you seen it? How during an eclipse, how the sun looks like? Have you seen it? A red ring-like structure. So that's basically nothing but the outermost part. And that is why the term corona. What is the meaning of corona? Anyone who knows it? What is the meaning of corona? The term corona, do you know that? Yes, crown, correct. So corona means crown. So during eclipse, it looks like the crown of the sun. So that is why the name corona has been given to the outermost part of the sun. So this reddish ring that you see is nothing but the atmosphere of the sun. So now what happens is that if we are in the atmosphere of the sun, it simply means that we have come far across from the core of the sun. So temperature should have decreased even further, because from 15 to 20 million degrees Celsius, the temperature has dropped to almost 5000 degrees Celsius by the time we have come to the surface of the sun, that is photosphere. So as we come towards the atmosphere of the sun, then in that case what happens? Temperature should have decreased further, but something opposite happens. What we see is that chromosphere has a temperature of up to 50,000 degrees Celsius, and corona could have a temperature of up to 1 to 1.5 million degrees Celsius. 1 to 1.5 million degrees Celsius could be the temperature of the corona. Now, why is this happening? All of a sudden, why is there a rise in temperature? The good thing is we don't know. The good thing is that we still do not know for sure why exactly does the temperature of the sun increase. And that is why there are researches happening. There are probes that have been sent. So for example, there is this Parker solar probe that was sent a few years back. Parker solar probe was sent, and this Parker solar probe, the primary objective is to understand the atmosphere and understand why this anomaly. Similarly, very recently, you know that we have launched our own mission, Aditya L1 mission. So Aditya L1 mission, one of the primary objectives of Aditya L1 mission is also to study the atmosphere of the sun and to understand why this temperature variation. What's happening there, which is causing such a huge variation and a sudden rise in temperature in chromosphere and corona. Right now, there are theories that why it should have happened, why these kind of things happen, but good thing is that we do not know for sure yet, and these probes or these missions that have been launched, probably they will give you some kind of explanation why the temperature suddenly starts to rise, right? so so this is about the region of the sun. Now when it comes to the sun, there are few phenomena that become very, very crucial for us: sunspots, solar flares, and solar winds. These are topics, or these are concepts that you will very, very often see in the newspapers as well. Every year, if you look at the newspapers, you'll see that at least there are 10 mentions of these concepts: sunspots, solar flares, and solar winds. The first picture that you see, this is the picture of a sunspot. This is the picture of a solar flare. And this picture signifies solar wind. All right. Sorry. So sunspots, solar flares, and solar winds. Now, in this particular case, just try to understand in very simple terms, what do we mean by these? First picture is of sunspot. So do you see that there are these spots that you have on the surface of the sun? These spots, or the darker color regions, they are called as sunspots. Now these are not small spots like pimples on our faces. These are very big regions. They can be bigger than the size of the earth, right? So these are called as sunspots. Now these sunspots, basically they can be formed sometimes when what happens is that sometimes what may happen is that a lot of energy is released out of the surface of the sun. So as soon as these energies or particles or heat particles are released, it leaves behind a blank space. It leaves behind a blank space where the temperature of this blank space could be in the range of, let's say, 3500 to 4500 degrees Celsius. So that is why this is a darker region, because the other parts of the surface is in the range of 5500 to 6000 degrees Celsius, and here the temperatures could be as low as 3500 degrees Celsius. So because of this difference in temperature, uh, compared to the surrounding parts of the sun's surface, we see that this appears as a darker region on the sun, and that's why it appears as a spot on the sun, or a pimple on the sun, where you apply Fair and Lovely and get rid of it. So sunspots, basically, that's why they are dark cooler areas that appear on the surface of the sun, right? Now this basically can be caused by intense magnetic activity on the sun's photosphere, or basically uh, the surface of the sun. And as I told you, the temperature can be in the range of 3500 to 4500 degree Celsius. So this is basically what we see in terms of sunspots. Now what we basically see is that from these kind of areas, the magnetic particles or energy particles, they are released out of the sun, and that is basically what causes this kind of sunspot. Now, one thing also to remember is that sunspots undergo cyclic changes known as the solar cycle, which lasts for around 11 years. What we basically mean is that uh, if a sunspot has appeared at this particular point, what you see here, 11 years later, at the same spot, at the same area, a sunspot will again re-emerge. 11 years. So that's why it is called as a solar cycle. That every 11 years, this cycle would repeat. This would come back and appear at the same point, at the same area. So that's why it is called as a solar cycle. And sunspots, they follow the solar cycle. Then after that, we have solar flares. Now, in case of solar flares, these are sudden explosions that are happening on the sun. All right, they are sudden explosions that occur on the sun, and they are occurring at the outer layer of the sun. They will emerge out of the outer layer of the sun, as you see like this. So a sudden explosion is happening on the sun. It is called as solar flare, and this solar flare is very, very big. Just look at the scale compared to the earth, how big a solar flare is. So a solar flare that comes out of the sun, emerges from the corona or the outermost layer of the sun, is a sudden explosion. Just remember the term sudden explosion, it's very, very crucial. All right, I'm just writing it here. It's a sudden explosion. So what happens here is that suddenly a lot of magnetic energy could be released, a lot of magnetic particles will be released from the sun, right? So this is basically what we see, and the energy would include X-rays and ultraviolet light, etc. And all these things, plus apart from that, a lot of charged particles like electrons and protons, they would also be present there. So a lot of charged particles like protons and neutrons will also be released from this particular solar flare. Now these solar flares, they can also have an impact on the earth. They can also have an impact on the earth. Not only solar flares, but even solar winds. Even solar winds will have a, if you look at this picture, so solar winds basically are magnetic winds. Now we are saying that in case of solar flares also, they are also magnetic in nature. In case of solar winds also, they are also magnetic in nature. So they are also being released from the sun. Solar flares are also being released from the sun. So what's the difference between the two? In case of solar flares, we are saying that this is a sudden explosion, right? In case of solar winds, it's a constant flow. It's a constant flow of charged particles from the sun. So they are also basically composed of protons and electrons, but at the same time we see that they also will be caused because of magnetic particles. So they are magnetic winds. So in a manner you can say that these are magnetic winds, magnetic winds continuously flowing, out of the corona. Continuously flowing out of the corona. So that's why continuous, constant is the key word here, because solar flare is sudden and solar wind is continuous. All right. So they will also be emitted out of the corona as we discussed, and now in this particular case they will also come towards the earth and they would also have an effect on the earth. And just remember that I'm just writing it here, both solar winds and solar flares can affect anything electrical, magnetic, or electronic on the earth, especially near the poles. All right. So especially near the poles of the earth, they will have an impact. They can have an impact. So this is where terms like auroras come into the picture, right? That they can create auroras. You might have heard of these terms: aurora, sorry, aurora borealis and aurora australis. Have you heard of these terms? Aurora borealis and aurora australis, the northern lights as we call for aurora borealis. So why the name aurora borealis? Aurora means what? Aurora is something related to colors, right? So we know that a green colored light is produced in the atmosphere whenever the solar activity is very high, especially in the north polar regions. You might see this, you might have seen the pictures probably. So aurora borealis. So why borealis? Because it is happening in the boreal region. What is the boreal region? Boreal forests you will probably learn about in geography or environment, either one of the two subjects. So boreal region is the Arctic region, correct? The Arctic region is also called as the boreal region. So that's why the boreal forests, they are basically the Arctic forest. So because it is in the boreal regions and it is producing colors, green colored light in the Arctic region, that's why aurora borealis. They could have called it uh, green light or northern light or something. Then in that case, the fun for somebody like me to explain that this is why they have named it. And scientists basically like making things complicated so that nobody outside their uh, community understands whatever they are saying. So so that's why aurora borealis is the name that they chose instead of a simpler name that they could have chosen. So aurora borealis and aurora australis, they basically, the primary reason for them would be the solar activity. If the solar activity is very intense, these lights or these colors will also be very intense. And the further they will be able to reach, it depends on the amount of activity. All right. Look at this question. This question was asked in your paper. Good days of elimination. Yes. Okay. If a major solar storm or solar flare reaches the Earth, which of the following are the possible effects on the Earth? First, GPS and navigation systems could fail. Now, GPS and navigation systems are satellite-based systems, so they are, you can say, electrical or electronic systems. So yes, they can fail. All right. So because we know that anything electronic can be affected. Anything electronic can be affected, and these are nothing but electronic instruments. So yes, they can. Tsunamis could occur. Now, tsunamis basically they occur because of what? They have seismic reasons, right? They would happen if an earthquake happens underwater or any seismic activity happens underwater, volcanoes erupt underwater, then they can lead to tsunamis. So it will not be caused by an outside magnetic effect because solar storm is magnetic in nature, right? So that's why we can't say that tsunamis could occur because of solar storm. And now see that you're already done. You have two here, you have two here, you have two here. So your correct answer is C. So that's why good old days of elimination method, which is probably not going to be of a lot of use in the coming papers. Uh, Third is power grids could be damaged. Perfectly possible because it is electrical and anything near the poles can be affected. So, for example, last year it was in the news that in New Zealand, a lot of power grids have been affected by a solar storm. So, that's possible. Intense auroras could occur over much of the earth. Is that possible? Yes, it is possible. And last year we have so many examples. This question came, oh, sorry, this year we have so many examples. In the month of April, I'm not sure whether you have read this. In the month of April, for the first time, in Leh region, in the Ladakh region, for the first time, we saw auroras. We observed auroras for the first time in even in Ladakh. Haven't happened before, but it happened before that in Britain, in London, etc. Also, you might have heard last year. I think September, October, it was in the news that it occurred because a huge solar storm had come towards the earth. So all these things have happened, so we know that yes, it is possible. And I really missed it. I was supposed to be in Ladakh when it happened, but last minute I had to cancel my trip. Otherwise might have been uh, I might have been able to observe it. Unfortunate, but such is life. Forest fires could occur, could take place over much of the planet. No, forest fires means what? That there has to be huge amount of heat. So these are not related to really huge amount of temperature or very high temperatures. Yes, solar flares can be related to heat particles, but they will not affect the earth. And even if they do, they'll first affect the poles and not much of the planet, right? And forget about forest fires. I mean, if let's say such intense heat reaches the earth, why would only forest fires will occur? We'll all get roasted. Correct. So that's why this is wrong. Orbits of the satellites could be disturbed. Yes, of course, as we discussed, anything electrical, electronic, magnetic, satellites can be disturbed. Shortwave radio communication of the aircraft flying over the polar regions could be interrupted. Absolutely correct. Polar regions will be the first ones to be affected. So that's why the correct answer 1, 3, 4, 6, and 7. So this question, easy question, it came in 2022. Next we have planets, but let's stop here. We'll start with this topic tomorrow. If you have any questions, please let me know. Let's look at your questions and then we shall end the session for today. Why the auroras will be seen in the at the poles first, and then after that they, if let's say they are strong enough, then probably they can be seen at the other parts of the earth as well. Otherwise mostly in the poles because of the magnetic nature. That nuclear fusion doesn't occur in the rate that it should. So the rate of nuclear fusion will start to decrease because it is continuously just losing out particles. So there will be a point that it would have lost so many particles that it almost becomes impossible for it to sustain anymore. And that is where you can see in a manner they start to die. The pink color largely is because of oxygen, and green color is largely because of nitrogen. And we know that our atmosphere is largely made of nitrogen and oxygen, almost 78% nitrogen and 21% oxygen. That's the primary reason why green color and why pink color. The black, we'll discuss this in tomorrow's class most probably. Pulsating, they would basically become brightened and darkened cyclically, and that's why they are called as pulsating stars. They are called as sunspots. All right, they would be called as sunspots, and they would occur because of magnetic reasons. All the three will happen because of magnetic reasons primarily. So now what happens is that maybe a lot of magnetic particles are released out of the surface. So surface is left with a darker patch on that area, and that's why sunspot. Then solar flare is a sudden burst of energy, a sudden burst of magnetic energy happening out of the corona. So that is basically called as solar flare. Many a times it is said that solar flares and sunspots are also sometimes related. Not always, not necessarily, but sometimes they do coincide as well. And then there is solar wind, which is a continuous flow of magnetic energy coming out of the sun, which is also coming out of originating, you can say, in a manner on the surface, but largely being formed out of the corona. There is no need to read the book. I would say that spend your time more on what we are learning here, plus on current affairs. Forget about any book. What we know that what has above the earth is universe, but what has under the earth is universe. I mean, see, above and under, you have this spherical earth, right? So if you're standing here, this is above for you. If you're standing here, this is above for you, right? So we cannot say that will not have the exact. Everyone with 50 and 60 points, be ready with a pack of sweets, and I'll send you my address where you have to send it. Devices in special cases will lead to electronic devices, so that's why anything electronic is also affected, because electrical and electronic both are basically similar. I mean, generally speaking, when we look at any yellow or whitish color in any star, it means that they have average temperature, that they neither have very high temperature nor they have very low temperature. When they are reddish in color, they have very low temperature. When they are bluish in color, sorry, when they are bluish in color, they have very high temperature. So that's nothing related to this. White color simply means that the temperature of our sun is average. Is basically what I was saying, that the origin, basically they begin from the surface, but actual formation really happens in the atmosphere. So that's why I think it's not very clear. So basically you can say this is mainly about the origin. This is where the origin is, and this is where the large formation is. Red giant. So red giant simply is nothing but a star which is very big in size. That's why giant. Red because it has very low surface temperature. There was a line on the slide of black hole which was conflicting, goes something like this: black holes have small area but are massive. So see, when we say massive, massive means that they have very large mass. Area is small, mass is very large. Understand this, there is no contradiction here. All right, we are saying that all the mass is concentrated in a very small area. That's why we are saying that they have very small area but are massive. Just imagine having a ball of cotton versus a ball of iron. So a ball of iron will have concentrated mass, will be massive in a small area. That is what we mean. Concept of black holes, where we say that this is an area from where a large amount of mass will be ejected out. So instead of mass being pulled towards a region, a lot of mass will be ejected out. will be called as white hole. Books are freely available on NCERT website. Go to the NCERT website, that is ncert.nic.in. Go there. There is a part called as publication. Click on publication. You will see all the PDFs are freely available for download there itself. So then eventually the light and the heat of the sun will decrease, but we can't see such something like this. It got suddenly. No, it will happen gradually, and it will take millions of years for this to happen. So the sun is going to outlive us all. So don't worry, we are never going to see this.